Welcome back to the Deep Dive. Today, we are taking a massive leap into, I think, one of the most mechanically and environmentally punishing sectors of heavy-duty transport. We're talking about the concrete mixer truck.
Oh, absolutely.
This isn't just about moving weight. This is about hauling a dynamic, hostile, and constantly hardening material across the roughest construction sites imaginable.
That's the perfect framing for this. I mean, the mission for this deep dive is to really unpack the comprehensive technical framework, the zero-base guide, if you will, that's required to transition these essential workhorses into the electrified era.
Right.
We are specifically looking at integrating a P2 hybrid system, and that's coupled with an electric power takeoff, or ePTO.
Hmm.
And it's all operating on a pretty high-stakes dual 24-volt and 400-volt platform.
Okay, let's unpack this. So we've synthesized a huge stack of engineering reports here. These are basically the foundational documents an engineering team would need to execute a complete system integration. Our job is to synthesize these and distill the critical pillars that, determine success or failure here.
And the foundational strategic insight, really the aha moment here, is recognizing and fixing the profound inefficiency of the traditional diesel mixer.
Okay.
Think about the scale of it. A traditional mixer uses this huge diesel engine, often rated between 150 to 300 kilowatts, and that's mainly to power the vehicle itself. But when it gets to the job site, it just sits there, idling, using all that massive power just to run a mixing drum that only needs about, 20 to 30 kilowatts for a steady rotation?
It truly is the definition of using a massive engine just to power an auxiliary system. It's like firing up a jet turbine to recharge your phone.
Precisely. That is a massive power mismatch, and it translates directly into wasted fuel, noise pollution, everything. By integrating this ePTO system, we decouple the mixing function.
So the engine can just shut off.
The electric motor handles the drum rotation, allowing the main engine to be completely shut down during loading, during mixing in transit, and especially during stationary discharge. And that quiet operation, it promises fuel savings from a guaranteed 25% up to a staggering 54% in those highly urban, idle, heavy-duty cycles.
So this is a business-critical move, not just an environmental one. We're solving fundamentally inefficient physics here. For this deep dive, we're focusing on the two main engineering deliverables that really define the success of this integration. First, the mechanical integration and 3D layout, which includes where we put everything and, crucially, how we route the sensitive high-voltage cabling.
Right.
And second, the absolute non-negotiable requirement, the thermal management strategy.
And these aren't just technical specifications. I mean, these two pillars, they represent the difference between a vehicle that runs reliably for a decade on a construction site and a system that fails catastrophically during its first high-pressure washdown or on its third high-heat stationary discharge cycle. We have to address the twin antagonists of mechanical stress and intense heat.
All right, let's start with the heart of the system then, the P2 architecture. For our listeners who might be familiar with mild hybrids and passenger cars, describe exactly where this motor sits in a heavy-duty vocational vehicle and why that placement is so strategic.
The P2 configuration is strategically chosen for its modularity. It has minimal intrusion into the existing heavy-duty powertrain. In simple terms, the electric motor is physically inserted between the internal combustion engine, the ICE, and the vehicle's transmission or gearbox.
And there's a clutch in there, right?
Yes. A key feature of the P2 is the inclusion of a disconnect clutch, which sits right between the engine and the electric motor.
And what does that clutch allow the system to do? What's the benefit?
It allows for incredibly versatile operation. It enables 4 crucial modes: pure ICE driving, pure electric driving if you have enough charge, a combined hybrid boost for acceleration, and critically, for vocational applications like mixers, it allows the engine to be completely decoupled and shut off while the electric motor runs the gearbox and, via the PTO, the mixing drum.
And that's how we eliminate that high idle fuel burn.
That's the magic right there.
So the source material details 2 primary physical approaches to P2 integration based on chassis constraints. Can you tell us about the trade-offs between on-axis and off-axis designs?
Certainly. The on-axis design is where the motor is directly in line with and integrated into the drive shaft. This is highly robust, it simplifies power transfer, and it's usually preferred for the highest torque, heavy-duty applications because it can handle significant shock loads.
But there's a downside.
The compromise, and it's a big one, is that it significantly increases the overall axial length of the powertrain. That can create serious packaging problems in an already space-constrained vocational chassis.
And the alternative? The off-axis.
The alternative is the off-axis or parallel shaft design.
Yeah.
Here, the electric motor is mounted alongside the main shaft and uses a system of gears or chains to transfer power.
So it's shorter.
Immensely. The benefit is that it significantly reduces the overall length, making it much easier to integrate into shorter chassis. It also lets engineers optimize the gear ratios specifically for the electric motor's speed and torque curve.
But there's a trade-off there too, I assume. More complexity.
Exactly. You have added complexity, weight, and a slight efficiency loss from the gears or chain drive system. It's always a trade-off.
Fascinating. Now let's tackle the power platform. We're using a dual voltage system. The legacy 24-volt domain and the new high-voltage 400-volt domain. I want to challenge the necessity of 400-volt system. Why can't we just scale up the 24-volt system to handle the load? Why do we need the complexity of 400V?
That's a fundamental engineering question, and it's all based on the physics of electricity. We require a continuous high power output. We're talking up to 45 kilowatts peak during concrete loading or discharge. To move 45 kilowatts of power at just 24 volts, the current required would be nearly 1900 amps.
1900 amps. That's staggering. I can't even imagine the cables for that.
It is. I mean, according to Ohm's law and I²R losses, that much current would necessitate enormous, extremely heavy, water-cooled cables. Think cables the diameter of your wrist. They'd be impractical, difficult to route, and subject to immense resistive sheet loss.
So running at 400 volts is primarily about reducing the current. What does that allow the engineers to do physically with the cable infrastructure?
It allows us to manage current efficiently. At 400 volts, that same 45 kilowatt load requires only about 112 amps.
Much more manageable.
So much more. This allows us to use much thinner, lighter, and easier to route cables. It minimizes material cost, weight, and resistive heat generation across the long runs of a truck chassis. The 400-volt domain, which typically operates between 270 and 450 volts DC, is absolutely essential for the high-torque, continuous work of the ePTO.
But the legacy systems, the brains and sensors, they still rely on 24V, right?
Absolutely. The Supervisory Controller Unit, or SCU, all the trucks CAN bus communication, safety interlock systems like the HVIL, and standard lights and accessories, they all still run on the robust 24-volt platform.
And how do you bridge those two worlds?
We bridge them using a high-efficiency DC-DC converter. This ensures the high-voltage traction battery continuously maintains the charge on the low-voltage auxiliary batteries. It's a crucial integration for maintaining critical functions, even if the HE system is disconnected for some reason.
Okay, moving from physics to safety. None of this integration can begin without mastering the global regulatory landscape. The foundation of safety integration is rooted in standards, and specifically UNECE R100 Revision 3. Why is this revision considered the international benchmark for high-voltage systems in new vehicles?
Revision 3 is incredibly influential, especially because it became mandatory for all new vehicle types in 2023 across regions that adopt ECE regulations. And that's most of the world, really, excluding North America, though its principles are followed everywhere.
So what's new about it?
It marks a significant shift from simply requiring physical protection to demanding sophisticated active safety and thermal protection measures. It's much more intelligent.
What are the absolute key takeaways from R100 Rev 3 that every engineering team must immediately adopt for a 400V system?
The first one is the most visual and simple. Mandatory orange identification for all Class B voltage wiring, so anything above 60 volts DC. This ensures immediate identification of lethal voltage circuits for emergency responders and maintenance crews.
That one seems obvious.
It is, but it's foundational. Second, protection against direct contact is paramount. Enclosures have to meet IPXXD or IPXXB classifications, which basically means internal HV components can only be removed with specialized tools. It prevents unauthorized access or, accidental contact.
And the most challenging update, which places a massive burden on the battery management system, is the thermal propagation and fire safety rule.
That's the real game changer. Revision 3 mandates that the vehicle's control unit must constantly manage the battery state to prevent thermal runaway. But the absolute safety rule is this. If thermal runaway does occur, the system is required to provide the occupants with a guaranteed minimum 5-minute warning period before smoke or fire can breach the cab.
5 minutes, that's a lifetime when you're talking about a battery fire. That must demand incredibly complex temperature monitoring and structural fire barriers.
It demands redundancy in temperature sensing, proactive software algorithms to detect early cell degradation, and often physical mitigation like highly resistant firewalls between the battery pack and the cab. This rule fundamentally drives the thermal management design. You're engineering for the possibility of failure, not just for success.
Beyond R100, we see some regional nuances. The
Mm.
sources highlight Japan's focus on potential equalization. Why is the requirement for resistance between any exposed part and the chassis to be less than zero point 0.1 ohms so crucial?
That extreme level of control, specified in Japan's attachments 110 and 111, is a mandate for perfect grounding. It's a measure of electrical safety integrity. The potential equalization ensures that if a fault does occur, say the HV wiring insulation chafes and touches the chassis, that energy is instantly and safely shunted away through that low-resistance grounding path.
So you're basically giving the electricity an easy path to ground that isn't the operator.
Exactly. A very low resistance means the fault current bypasses the person and immediately trips the protection system. It minimizes the risk of touch voltage. And achieving less than zero point 0.1 ohms requires rigorous auditing, using robust grounding straps, and ensuring zero corrosion at all chassis connection points throughout the life of the vehicle.
And quickly, China's GB3A032 standard. It's often used as a reference for durability.
Yeah.
What does it emphasize for these vocational vehicles?
China's standard really focuses on extreme ruggedization. Given the vast and often challenging operating environments there, the standard mandates specific severe water immersion tests and rigorous fire resistance protocols that can exceed the general R100 requirements. It's a reflection of designing for maximum abuse, which makes it a great reference for any high durability product like a concrete mixer.
Okay, we've established the safety rules. Now we have to face the real enemy. Physics in motion. We're moving from the regulatory framework to the physical challenge of integrating heavy, sensitive, high-voltage components onto a vocational chassis. So how do you bolt an expensive, rigid 400-volt battery housing onto a structure that, moment to moment, is fighting against itself?
This is the absolute core mechanical hurdle for all vocational electrification. A truck chassis is not a rigid beam. Especially on rough construction sites, it undergoes massive torsional forces. Engineers call it scissoring or laddering. When one wheel is high and the diagonally opposite wheel is low, the frame rails literally twist independently of each other.
And if you rigidly connect a heavy battery pack, which is essentially just a stiff metal box to two frame rails that are twisting, what happens? I can't imagine it's good.
It's disastrous. The torsional loads are transmitted directly into the battery housing or the inverter casing. Over thousands of miles and hundreds of duty cycles, this stress leads to accelerated fatigue. It manifests as microfractures in the aluminum housing, premature failure of the enclosure seals, or strain on the internal cell connections. This means compromised safety and a dramatically reduced service life.
So the solution is to decouple the component rigidity from the chassis flexibility. Tell us about the engineering solution for this, the kinematic mounting strategy.
Kinematic mounting is absolutely mandatory. It's the strategy of using spherical, self-aligning bearings, flexure plates, and integrated vibration isolators to connect the rigid electric superstructure, the battery box, the power distribution unit, to the twisting chassis frame.
So the component basically floats.
In a way, yes. This ingenious design allows the chassis to twist freely underneath the component. The component stays level and planar while the steel frame warps around it.
So the mounting system absorbs all that relative displacement, the pitch, roll, and twist, without transmitting those destructive bending stresses to the rigid housing.
Exactly. This is non-negotiable for battery packs, which can range from 100 kilograms to 6,000 kilograms in heavy-duty applications. You are protecting millions of dollars worth of battery cells from pure structural failure.
Let's discuss the physical placement or the zoning strategy. Where are these components ideally situated on the truck?
For both thermal protection and physical safety, the preferred location is typically the back of cab or both C. This positioning offers protection against side impacts and minimizes exposure to road spray. And crucially, it maximizes separation from the engine's high thermal load.
And there are strict rules about clearance, right?
Oh, absolutely. We maintain strict adherence to clearance rules, a minimum of 10 millimeters from all stationary parts and 25 millimeters of dynamic clearance from anything that moves, like suspension components or drive shafts.
Okay, so we move now into the highly disciplined requirements for 6.1, the high-voltage harness routing. This is a critical safety pillar. What defines proper routing beyond just using bright orange wiring?
Well, the ideal harness routing follows the proximity principle. Use the shortest path to save weight and minimize resistance. But safety and reliability rules override everything else. The primary mandate, the one that causes the most packaging headaches, is the 400 millimeter separation principle.
400 millimeters, that's nearly 16 inches of distance. That is enormous, on a truck chassis where every single inch of space is fought over.
It is a massive spatial requirement, and it is mandatory for electromagnetic compatibility, or EMC. We must maintain a parallel distance of at least 400 millimeters between the high voltage orange harness and the low voltage 24V signal or CAN harnesses.
And what happens if the engineers fail to maintain that separation? What's the consequence of this EMI coupling?
The high-frequency noise that's generated by the motor's inverter is suppressed by the harness shielding, but if the LV and HV lines run parallel and too close, capacitive or inductive coupling occurs.
And that corrupts the signal.
It can corrupt the sensitive low-voltage signals, it could disrupt the SCU's ability to read critical sensor data, cause the CAN bus to malfunction, or lead to unintended system behavior. Things like a sudden torque surge or the drum starting unexpectedly, it's a huge safety risk.
So if you absolutely have to cross them,
If crossing is unavoidable, it must be performed at a 90-degree perpendicular angle. This minimizes the coupling area to a single point.
beyond EMC, the mechanical protection in this hostile environment is critical. Construction sites are full of debris, dust, and temperature extremes.
Absolutely. So the harness has to be routed away from heat sources, specifically the exhaust system, by a minimum of 200 millimeters. All HV cables must be encased in high-temperature, mechanically resistant corrugated pipes. But here is probably the most important small detail. For every single chassis passer, every time the cable goes through a metal frame, you must use a rubber grommet specifically specified at 0.5 millimeters minimum thickness.
That specific 0.5 millimeter detail tells you that this failure mode has been experienced many, many times.
It has. That simple rubber grommet prevents metal-to-wire chafing. Over the operational life of the vehicle, constant vibration would wear through the insulation, leading to a high-voltage short to the chassis. That's a potentially catastrophic safety event. It's cheap insurance against a total vehicle failure.
And fixation. Managing vibration and stress relief.
Yeah.
How often do we need to secure these large, heavy cables?
Fixation is key to longevity. Large cables, which we define as those greater than 16 square millimeters in cross-section, must be secured with clamps every 200 to 300 millimeters maximum. This is crucial to prevent the cable from developing its own natural resonant frequency, which can accelerate insulation fatigue.
We're fighting vibration everywhere on this thing.
We are, and here is a non-intuitive mechanical rule. You must maintain a perfectly straight, unbent path of between 100 millimeters and 120 millimeters from the connector exit to the first fixation point.
Why that specific straight path requirement right at the connection point? That seems odd.
It's to prevent stress concentration. That small, straight section acts as a strain relief zone. If you clamp or bend the cable too close to the connector, the vibrational forces concentrate right at the terminal interface.
And that leads to breaks.
It leads to microfractures in the internal conductor strands, or, more commonly, it compromises the integrity of that crucial rubber wire seal where the cable enters the connector housing.
And what about bending the cables themselves? You can't just shove these stiff, shielded bundles into sharp corners.
No, absolutely not. The minimum bend radius for these high-voltage shielded cables has to be at least 5 times the outer diameter, so 5XOD. Bending them any tighter risks crushing the internal strands, compromising the insulation layer, and critically damaging the essential shielding braid that wraps around the conductors. And that brings us to the shielding details. We need total suppression of high-frequency noise, which means the shield isn't just a jacket, it's a critical safety feature.
Absolutely. So the mandate is the use of braided copper shields with a coverage ratio of at least 90%. And to ensure this noise is completely contained and shunted away, you have to maintain 360-degree shielding continuity.
Yes, and this is achieved by using specialized 360-degree shielding rings or clamping rings at every connector interface. This ensures the shield material is perfectly bonded to the connector's metallic backshell and ultimately grounded to the chassis.
So what's the target?
We're aiming for CISPR 25 Class 5 compliance. That's the highest electromagnetic emissions requirement for safety-critical automotive systems like the SCU. Any compromise here means immediate failure in the field. And again, this links right back to the potential equalization. That perfect low-impedance grounding below 0.1 ohms is the only way to ensure the shield works as intended.
Okay, so if torsional stress is risk A, then the high-pressure chemical washdown is risk B. And it's pretty unique to this vehicle. We need to protect multi-thousand-dollar sensitive power electronics from concrete slurry and extremely aggressive cleaning procedures.
The environment is uniquely hostile. I mean, concrete is highly alkaline, the abrasive dust is conductive, and the cleaning involves high pressure and often caustic or acidic agents. We cannot rely on standard automotive IP67 protection. It just fails under high pressure and temperature swings.
Let's define the gold standard here, IP6K9K. What level of physical violence must an enclosure withstand to get that rating?
IP6K9K signifies the pinnacle of durability for washdown environments. The 6K confirms it is completely dust-tight, which is critical against conductive concrete dust. The 9K requires resistance to high-pressure, high-temperature jets.
And we have the specific test conditions required by the regulatory body.
We're talking about water jets delivered at 8,000 to 10,000 kilopascals of pressure. To put that into perspective, that's roughly 100 bar, or the equivalent pressure of an industrial fire hose being sprayed at close range.
Wow.
And what's more, the water temperature has to be high, 80 plus or minus 5 degrees Celsius. The test is rigorous, spraying the component from 4 distinct angles for 30 seconds each.
Now, let's address the hidden enemy that causes most standard IP-rated enclosures to fail this test, even if the seals look perfect: the thermal breathing effect.
This is the critical piece of physics that most initial designs miss. During stationary operation, the motor, the inverter, the battery, they're all generating heat. This causes the air inside the sealed enclosure to expand and create a positive internal pressure.
Okay.
Then the operator finishes the shift and immediately blasts the component with that 80-degree water. Even though the water is hot, it rapidly cools the enclosure casing.
And that rapid external cooling causes the air inside to contract instantly.
Correct. That sudden contraction creates a dramatic internal vacuum, a negative pressure that can drop by up to 200 millibar inside the enclosure. If you rapidly cool a sealed jar, the vacuum effect sucks the lid in. In this case, the vacuum literally sucks moisture, condensation, and even trace contaminants right through the tiniest imperfections in the gasket, or past the wire seals.
That's how components drown.
That is exactly how they drown.
So what's the engineering solution to neutralize this pressure differential without compromising the seal?
The key solution is integrating ePTO waterproof breathable membranes, or vents. These are small, specialized inserts built directly into the housing. They're essentially Gore-Tex-like materials with micro holes that are incredibly small, about 0.2 micrometers wide.
Tiny, tiny.
It is. The holes are small enough to create a physical barrier that liquid water molecules and dust particles cannot pass through, but they are large enough to allow air molecules to pass freely.
So it lets the box breathe.
Exactly. This process continuously equalizes the internal and external pressure, preventing that catastrophic vacuum, the thermal breathing effect, from ever developing. It ensures the seal integrity holds up against both thermal shock and high pressure.
Let's move to sealing and material science. Concrete is pH 12, highly alkaline. Standard seals won't survive this. What materials are mandatory for gaskets and seals?
We have to move away from standard materials like NBR, which is nitrile butadiene rubber. It rapidly ages and cracks under UV exposure and chemical attack. The mandatory specification calls for high-performance elastomers such as FKM, fluorocarbon rubber, often sold as Viton or high-consistency silicone rubber.
And what do those give you?
These materials offer chemical resistance to the alkaline concrete, resistance to acidic cleaning agents, and they maintain seal elasticity across a massive temperature range, from negative 40 degrees Celsius up to 150 Celsius.
And the physical design of the seal is as important as the material. You need structural integrity against 100 bar of pressure.
Absolutely. For large enclosure gaskets, engineers must use tongue and groove profiles. This ensures that when the screws are tightened, the gasket is mechanically captured and cannot bulge or be displaced when subjected to that 100-bar water jet. We also mandate the avoidance of sharp 90-degree internal corners in the enclosure design.
Why is that?
Rounded gradual corners are far better for distributing stress and pressure. Sharp angles are inherent leak initiation points. It's just bad design.
We must also manage corrosion. Aluminum is a common housing material, but it reacts poorly with highly alkaline concrete.
That's a major risk. Bare aluminum will rapidly corrode when exposed to concrete slurry. The mandatory surface treatment is multi-layered. The aluminum must first be chemically or electrochemically anodized, which creates a hard, protective oxide layer.
But that's not enough on its own.
No. Then it has to be covered with a robust protective powder coating. Both layers are necessary to ensure 20,000 hours of service life.
And the problem of galvanic corrosion. If we use standard stainless steel fasteners in an aluminum casing, we basically create a microbattery.
That potential difference, the noble stainless steel reacting with the less noble aluminum, promotes rapid corrosion right at the interface. To prevent this, a fundamental mitigation strategy is isolation. We must use nylon or PTFE washers to electrically isolate the stainless steel screws from the aluminum enclosures.
I see.
For external fasteners exposed to road salt, we often specify GMA-coated carbon steel because its electrical potential is much closer to aluminum. It minimizes the galvanic risk while providing excellent salt spray resistance.
Finally, let's tie this physical protection back to safety with the high-voltage interlock loop, or HVIL, integration. How does the mechanical design of the connector housing dictate the speed of the electrical safety response?
The HVIL is the non-negotiable ultimate safety mechanism. It's a low-voltage sensing circuit that runs sequentially through every single high-voltage connector and service disconnect. And the mechanical design of the connector interface is paramount.
Specifically, the length of the pins.
Exactly. The pins carrying the low-voltage HVIL circuit must be engineered to be shorter by at least 2 to 3 millimeters than the main HV power pins.
And why is that?
This ensures that if the connector is even slightly pulled, or if a high-pressure jet manages to breach the front seal and reach the pins, the shorter HVL pin disconnects before the longer, lethal 400 V power pin.
So the safety circuit breaks first, triggering the de-energization.
Correct. Breaking that low-voltage HVIL loop sends an immediate hard signal to the SCU. The system must then execute an emergency discharge of the 400 V bus, and the regulation mandates that the voltage must drop below 60 V DC within a single critical second. The mechanical layout of the pins determines if we meet that 1-second safety standard.
Okay, we've mastered the mechanical stresses and the environmental protection. Now for the final engineering pillar. How do you maintain continuous high-load output in the most challenging thermodynamic scenario when the truck is static? We're tackling deliverable 0602, the thermal management strategy.
The thermodynamic reality is governed entirely by the worst-case scenario: zero vehicle speed, high torque load. This is typically during stationary concrete discharge, often coupled with high ambient heat, say 40 degrees Celsius or higher.
Right, a traditional vehicle would benefit from ram air when it's moving.
But mixers lose that benefit precisely when they need maximum power.
How significant is the heat load we actually have to manage?
Even modern, highly efficient power systems shed significant heat. A mid-range 50-kilowatt ePTO motor operating at a very good 95% efficiency still sheds 2.5 kilowatts of heat. You add in the inverter and battery losses, and the total heat rejection capacity needed for the electric superstructure is typically 6 to 8 kilowatts continuous.
And if that heat isn't removed instantly?
If it's not removed, the motor windings and power electronics rapidly exceed their thermal stability limits.
And what's the consequence of exceeding that thermal limit? What actually happens?
For the motor, excessive heat causes insulation breakdown, rapid demagnetization of the permanent magnets, and permanent loss of efficiency or even catastrophic failure. For the inverter, it significantly reduces the lifespan of the sensitive silicon carbide, or SiC, modules. This is why air cooling is fundamentally rejected for this application.
For two core reasons, right? Dust and just pure heat capacity.
Exactly. Construction site dust rapidly plugs air cooling fins, killing efficiency. But more importantly, liquid cooling, specifically a water glycol mixture, is vastly superior. Glycol-based coolant has a heat capacity up to 3,500 times higher than air. It's the only viable method for continuous high-power rejection.
So we need to design an independent, low-temperature, or LT loop. We cannot, under any circumstances, share the engine's coolant. Why is the engine coolant temperature so detrimental to the electric system?
The diesel engine's loop is optimized for its own efficiency, and it runs hot, typically reaching 105 to 115 degrees Celsius. That heat is fundamentally lethal to power electronics.
They just can't handle it.
No. Inverters, particularly those using advanced SiC technology, perform optimally and achieve their long design life when they operate cool. Introducing 115-degree coolant would immediately compromise performance and reliability.
So we need a dedicated separate LT loop. Walk us through the optimal thermal sequencing within this new loop. Which component gets the coldest coolant first?
The architecture has to ruthlessly prioritize the most sensitive components. The sequence starts with the 24-volt PWM-controlled electric water pump, which provides a high flow rate of 20 to 30 liters per minute. The coolant goes immediately from the pump to the inverter cold plate.
The inverter gets priority. Why?
The CST power modules are the most delicate link in the chain. Their reliability is highly sensitive to junction temperature swings. We aim to keep the coolant entering the inverter in an ideal band, typically 15 to 35 degrees Celsius.
And then it goes to the motor.
Correct.
No.
From the inverter, it proceeds to the motor jacket, and only then does it go to the radiator to reject the heat. The electric motor, with its high-grade winding insulation, can tolerate the slightly warmer coolant exiting the inverter, making this a thermodynamically optimized series flow sequence. And the radiator has to be robust, with a reversible fan function to allow for periodic dust blowout on site.
Here's where the software provides the safety net. The intelligence of derating. If the thermal system is overwhelmed on a 45 degrees Celsius day, we can't just shut the mixer off.
No, an abrupt shutdown is a severity 8 catastrophic failure for a mixer. The concrete hardens rapidly, resulting in the loss of the load and potential damage to the drum and gearbox.
So the system has to be smarter.
The system must employ proactive derating. The SCU constantly monitors the winding, IGBT, and CC module temperatures.
How does that derating process actually work? What does the operator experience?
As the component temperature approaches its critical limit, the SCU doesn't just throw a breaker. Instead, it gradually and linearly reduces the maximum available torque the electric motor can output.
Nice.
This allows the system to continue maintaining drum rotation, even if it's at a lower, less energy-intensive speed, which is critical to prevent the concrete from seizing. It's a graceful degradation instead of an abrupt system-damaging thermal shutdown.
Let's delve into advanced cooling techniques for a moment, specifically for those concentrated heat fluxes generated by the CC inverters.
Right, SECI enables immense power density, but that means concentrating intense heat in very tiny areas. To handle this, standard cold plates aren't enough. Advanced designs have to feature internal structures, like mini-channel manifolds, or utilize perpendicular jet flow. These techniques dramatically increase the contact area and turbulence between the coolant and the heat source.
Give us a sense of the scale of performance improvement this offers.
We're aiming to achieve extremely high heat transfer coefficients, sometimes up to 93,000 watts per square meter Kelvin. To put that in perspective for the listener, that efficiency is hundreds of times more effective at pulling heat away than if we just blew air over the top of the inverter housing. It's microengineering solving a macro power problem.
We also have to consider the opposite extreme, the cold start strategy in sub-zero environments.
Absolutely. In deep winter, battery cells struggle to deliver full power, and the lubricants, both in the motor gearbox and the main drum gearbox, become incredibly viscous. It can make rotating a loaded drum nearly impossible.
So the system has to work in reverse.
It does. We use high voltage positive temperature coefficient, or PTC, coolant heaters, typically sized between 3 and 10 kilowatts.
And what are they preconditioning? What are they warming up?
They precondition two things. First, the battery cells, warming them to an optimal temperature around 10 degrees Celsius so they can accept and deliver high current. And second, they warm the drum gearbox oil. This preconditioning is essential for delivering the immediate high torque capacity needed to start rotating a cold, heavy load on a winter morning.
Now we get to the digital slump monitor. This is where the electric system truly transforms the mixer from, a mechanical slave into a constantly calibrating physics lab.
This is one of the key value adds of electrification. The electric motor, unlike a diesel engine that only provides gross torque data, is an inherently precise sensor. By continuously monitoring and correlating the motor current, the voltage, and the drum rotation speed, the supervisory controller unit can calculate the resistance the drum is facing. And that resistance directly correlates the consistency of the concrete at slump in real time.
I see. So the system knows dynamically if the concrete is getting stiff.
Exactly. If the slump drops, meaning the concrete is stiffening prematurely, the torque requirement to maintain a constant drum speed spikes instantly.
And that's not just a quality alert.
No, that detected torque spike is also a thermal load spike that gets signaled to the SCU. The system can then proactively respond, increasing the pump and fan speed before a thermal limit is reached, or, crucially, alerting the operator to add water or plasticizer to maintain quality, preventing the load from being ruined. It turns data into proactive thermal and material management.
We've engineered this incredibly complex system, but now we have to prove it won't fail. The roadmap demands a robust failure analysis, starting with FMEA, failure modes and effects analysis. When we look at mechanical and thermal integration, what are the high-severity failure modes that keep you up at night?
When we conduct the FMEA, we're looking for items with severity 9 or 10 ratings. The first critical mode we always address is harness abrasion.
Which is caused by the chassis twist exceeding the motion envelope, right?
Precisely. The kinematic mounting, or the harness fixation, failed to account for extreme torsional movement, leading to long-term rubbing against the chassis. The effect is insulation failure, leading to a high-voltage short to the chassis structure.
And that is a
That is a severity 10 risk. It requires immediate, extreme mitigation and redundancy.
The next major risk involves the thermal loop itself.
Active cooling loss. If the electric pump fails, or if a hose is severed on the construction site, the system rapidly loses its ability to shed heat. The effect, specifically for a mixer, is motor derating, followed by complete thermal shutdown, which leads immediately to concrete hardening.
And that's a
Severity 8 event, total loss of the expensive load and potential damage to the mechanicals.
And finally, a mechanical failure tied directly back to our kinematic solution.
Kinematic mount wear. This failure mode is often caused by long-term resonant vibration at specific chassis speeds, leading to fatigue failure in the bracketry. The high-severity effect is structural failure, leading to the battery housing cracking and potential electrolyte leakage. That's a severity 9 event due to the dual chemical and electrical hazard.
So what are the mandatory mitigation strategies for these critical risks? How do you engineer them out?
Mitigation requires redundancy and absolute compliance auditing. For thermal risk, we need redundant temperature sensing, using the motor's internal winding thermistors alongside coolant temperature sensors. For abrasion, we rely on the mechanical rules we discussed, and we mandate rigorous grounding audits, verifying the resistance remains below 0.1 ohms across the entire system.
And a software check.
And absolutely essential, software-based HVIL integrity checks must run before the system is allowed to energize the 400V bus at the start of every single shift.
Let's trace the engineering path, the V model. You can't skip straight to bolting things onto the truck. We start with phase 1, virtual prototyping.
The V model is essential for de-risking a zero-based design. Virtual prototyping requires high-fidelity modeling. We use finite element analysis, or FEA, to optimize the structural components, checking the side rail integrity, confirming the stiffness of the kinematic mounting brackets, and crucially, reducing mass while maintaining strength against torsional loads.
And for the thermal system, we rely on computational fluid dynamics, or CFD. What does the CFD simulation look like in practice for the specific vocational vehicle?
We simulate the absolute worst-case operating point. The model has to verify fluid flow and heat transfer under the scenario of static full load plus 40 degrees Celsius ambient temperature. We verify that the thermal interface materials between the components and their cold plates meet a minimum thermal conductivity target, typically at least 5 watts per meter Kelvin. That ensures heat is efficiently passed from the power module to the coolant.
Then we move to phase 2, hardware in the loop, HIL, and bench testing. This is where the virtual meets the physical without risking a full truck.
Exactly. Verification of the thermal design has to happen off-vehicle first. We run the motor and inverter through full duty cycle simulations on a specialized test bench, monitoring the precise heat rejection rate and verifying that the LT loop components can sustain that 6 to 8 kilowatts of heat load without triggering derating.
And the mechanical side.
We subject the HV battery housings to punishing crushing tests and hundreds of hours of sinusoidal vibration sweeps to confirm the mechanical integrity under extreme accelerated fatigue conditions.
Finally, phase 3, commissioning and audit. What are the mandatory sign-off requirements before the vehicle goes to market?
Final sign-off is non-negotiable and requires a mandatory HV audit. The key metric is confirming the de-energization time. The 400V bus must physically drop below 60 VC within 1 second of the operator, triggering the service disconnect or a breach of the HVL.
And the water tests.
And the entire vehicle also undergoes the IP9K high-pressure spray testing in a certified lab to confirm that every seal, connector, and closure can handle the real-world washdown environment.
To bring this all into context, let's look at the benchmarks. How are the major market leaders integrating these systems? And what engineering choices are they prioritizing?
The industry leaders show diverse, optimized strategies. Liebherr, with its ETM series, often utilizes a slightly higher 650-volt platform and, interestingly, integrates the large battery pack directly within the subframe structure. This choice optimizes axle load distribution and keeps the pack low.
And Sany's approach, they focus more on the chassis modification itself.
That's right. Sany's e-mixer employs a no subframe structure concept. This requires complex chassis engineering, but the profound benefit is that it significantly lowers the overall center of gravity by anywhere from 130 to 200 millimeters.
And that's huge for stability.
It drastically enhances the roll stability of these massive, top-heavy vehicles, a major safety concern on uneven terrain.
And Sifa Energia seems to focus heavily on energy recuperation.
Yes. They prioritize a plug-in concept, often using independent modular battery packs, and they integrate a kinetic energy recovery system, or KERS, specifically for the drum. They use the drum's deceleration, that slow-down moment, to regenerate charge, adding a layer of efficiency you'd typically see in passenger vehicles. Each leader has found a specialized engineering path, but they all share that commitment to advanced thermal and mechanical mastery.
What an incredible deep dive into the engineering required just to make an electric mixer viable. I mean, the core value proposition here isn't just electrification. It's the mastery of three critical engineering pillars. First, managing portional mechanics, using those sophisticated kinematic mounts to protect heavy, rigid components from the twisting chassis.
Yep.
Second, guaranteeing high-voltage safety and EMC performance through rigorous harness routing rules, like that non-negotiable 400 mm separation. And third, maintaining continuous high power in static high-heat scenarios using the independent LT loop and proactive derating.
And if we connect this to the bigger picture, the entire future of construction logistics is becoming irreversibly digital. The ePTO system is the catalyst for that.
How so?
By leveraging the electric motor as a high-precision sensor, the digital slump monitor provides real-time, non-invasive material quality control. This transition moves the concrete mixer from a simple mechanical device driven by brute force to what is essentially a constantly calibrating physics lab on wheels.
And that data has value.
It provides data that can be used for liability tracking, predictive maintenance, and quality assurance. It's a total game changer.
Here's where it gets really interesting, building on that benchmark analysis. You mentioned Saudi achieving a huge safety gain by lowering the center of gravity by hundreds of millimeters through structural changes. This brings us to a final provocative thought for our listener to consider. The next major evolution in this heavy-duty field is the shift toward axial flux motors for the ePTO application.
That is the future of power density for vocational vehicles, absolutely. Unlike traditional radial flux motors, axial flux motors are disc-shaped. They're much flatter and more compact relative to their power output.
Why do these compact, flat motors matter more for these top-heavy concrete mixers than they might for, say, a standard passenger car?
Because space and weight distribution are the ultimate trade-offs in a concrete mixer. Their superior power density and compact form factor allow the entire ePTO unit, and subsequently the battery packs, to be positioned lower or integrated more seamlessly into the subframe.
So it's all about that center of gravity.
Every single millimeter you lower the center of gravity on a concrete mixer. A vehicle inherently designed to haul rotating mass high off the ground significantly improves its roll stability, enhances maneuverability, and drastically increases the safety margin during cornering and off-road operation. That mechanical and safety gain is arguably the single biggest driver for adoption.
A flatter, lower motor for a safer, smarter, more efficient truck.
That is a brilliant piece of systems architecture to conclude with. Thank you for guiding us through the complexities of mechanical and thermal mastery in this heavy-duty hybrid world.
My pleasure. The zero-base engineering required here is truly world-class.
And thank you for joining us for the deep dive. We'll see you next time.